part 1 is on simplifying radicals. So these are the basic radicals that you should have seen like in Algebra 1 even. So there's lots of different ways to simplify radicals. So I found that most of my students kind of want a straightforward way of doing this. And so one of the things that works is to use a factor tree. Can you put that away? So if I had the number 72 and I wanted to try to find the square root of 72. Okay, one way to do this, it's kind of a longer way, but would be to write out 72 and write its factors, 8 and 9, and then say, okay, 8 breaks down into 4 and 2, and 4 breaks down to 2 and 2. So we end up getting the prime factorization of 2 cubed times 3 squared, right? So we have 2 times 2 times 2 times 3 times 3. Okay, so what a square root asks is for you to find pairs of items, basically, pairs of factors. Okay, so if I circle the pairs of items, I have 2 2's and I have 2 3's. And then I have another 2 that's just all by itself. Okay, so let's think about this. What is 2 times 2? 4. What's the square root of 4? 2. So when I take the square root of one of those pairs, I'm left with only a single thing, right? So instead of having 2 times 2, I just have one of the 2's. Does that make sense? How about this one? So what's the square root of 3 times 3? So the square root of 9 is 3. Okay, so what we do is we think about our square root of 72, and we break it into the square root of 2 times 2, which was 2, the square root of 3 times 3, which is 3, and then the other one is all by itself. This doesn't have a pair. Okay, so the one that doesn't have a pair gets left inside the square root. Okay, so we have 2 times 3 on the outside, and then times square root of 2. So our answer should be 6 root 2. Okay, so that's a pretty straightforward way of simplifying radicals. Okay, there are easier ways, but let's start these out like this. Now, number 1 and number 2, I hope that you guys all know. Okay, so you should know these anyway. Do you guys agree? You all know these? What's number 1? 8. Oh, Michael. And what's number 2? 12. Such a prankster. All right, so if I was breaking apart 64, I could break it into 8 and 8, and then 8 breaks into 2 times 2 times 2, and 8 breaks into 2 times 2 times 2. So the reason that the square root of 64 is 8 is because it's 2 times 2 times 2 in the end, right, which is 8. So you don't have to do it that way on things that you know. So like number 2 we just said was 12. So please don't do the factor tree method if you actually know how to take the square root. So 32, though, does not have a square root. And I don't want you guys to just say, oh, it's like 5 point blah, 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 blah. I don't want decimal approximations. I want what's called blah, 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 you like that. I want what's called exact values. So exact values involve the square root, irrational numbers. Okay, so if I have the square root of 32, I want to simplify it down, and there's still going to be a square root. Okay, so I think about what goes into 32, maybe 4 and 8. 4 breaks into 2 times 2. 8 breaks into 2 times 2 times 2. So I have a total of 5 2's. Yeah, Cole, do you have a question?
If you have if you just have a 4, you already know that's 2 2's. You just stop there.
Yeah, you could, yeah. And then we circle, we say we have a pair of 2's, a pair of 2's. So our answer should be a 2 on the outside, another 2 on the outside from the second pair, and then 1 2 left on the inside. So it should be 4 root 2. Make sense? So there's faster ways of doing this. So we'll do this in a second, but let's do a couple more. So 124. So 124 we can't take the square root of evenly, okay? So I break it apart, and I'm like, okay, well, what goes into it? I always help like 4th and 5th graders with prime factorization trees, and it always cracks me up because they always do 2. That's okay. So we're going to do 2 on this one. And we have 62, right? And then 2 goes into it again, and we have 31.
Yeah, she was a little disappointed that there wasn't more.
Oh my gosh. All right, so we end up getting 2, 2, and 31. So we have a pair of 2's. So when I take the square root of 2 times 2, square root of 4 is 2. And then the square root of 31 is left how it is because 31 is prime. So the square root of 124 we would simplify as 2 root 31. All right, 1024. This is another one that a lot of people will do, 2, 2, 2, 2. So anybody know what the square root of 1024 is? Anybody know the answer? Yeah. Well, we'll see. All right, so 2 and 512, 2 and 256, 2 and 128, 2 and 64. All right, let's stop doing the 2 and 2. We're getting a very lopsided tree, right? So how about 8 and 8? And 8 breaks into 2 times 2 times 2. And the other 8 is 2 times 2 times 2. So I have 6 2's from just the 8s there. There's the 7th 2, 8th 2, 9th 2, 10 2's. So 1024 is 2 to the 10th. So if I have 10 2's, how many pairs of 2's do I have? Yeah, I have 5 pairs. So I'm going to have 2 to the 5th out front. So 2 times 2 times 2 times 2 times 2. So what is 2 to the 5th? 32, exactly. So the square root of 1024 is 32. All right, so this kind of takes a long time on some long ones, right? The 1024, that was kind of a lot. Okay, so there's another way of doing these, so we're going to talk about it. So another way of doing this without doing the factor trees is to think about the largest factor, so the biggest thing that goes into, for example, 500. That's what we call a perfect square. Okay, so perfect squares are numbers like 1, 4, 9, 16, so it's 1 squared, 2 squared, 3 squared, 4 squared, 25, 36, 49. All of these numbers are perfect squares, 64, and so on. Some of your teachers had you memorize perfect squares, which I appreciate when teachers have you memorize perfect squares. All right, so if I have 500, I know one of the perfect squares that goes into it is 25. Can I go bigger? Yeah, what? 100. Okay, so instead of doing the factor tree, what you could do is you could say, well, I know the square root of 500 breaks into 105, right? So I have the square root of 100 and the square root of 5, and together make square root of 500. And we know what the square root of 100 is. So the square root of 100 is 10, and then 5 stays just as it is. Now, if 5 had now been like 25, then you would continue to break down, or 45, you'd continue to break down, okay? But in this case, we just stop because we have our perfect square out front and then root 5. Not perfect square, but the square root of the perfect square. All right, so if I have multiplication, so if I have square root of 20 times square root of 5, I can combine. And that's kind of, I did the opposite on the last one. I broke it apart into separate ones. So this is going to be the square root of 20 times 5, which is the square root of 100. So it's going to be 10, yep. All right, so the same idea on this next one. It's going to be square root of 2 times 18, which is 36, all over 3. So Eric's saying the square root of 36 is 6, so 6 over 3. So we end up getting the answer of 2. Is making sense? It's really not a bad section. Easy one to end the week on for a long weekend, right? All right, so the next one, if I have 4 over root 2. So we have a lot of strange rules in math. So I told you guys at the beginning of the year that things like 7 over 2, you could just leave as 7 over 2. But you guys remember in Algebra 2, you guys always wrote it as 3 and 1/2. Like in Algebra 1, I mean. But once you get to Algebra 2, we don't care. You can leave it as 7 over 2. Okay, the same thing is kind of like for this next one, 4 over root 2. Okay, we don't like that. We don't like when it's 4 over root 2. Okay, we don't like square roots on the denominator. Have you guys seen this before? Yeah, so we don't keep square roots on the denominator. We do something that's called rationalizing the denominator. A lot of times you guys do this in geometry classes, because we have a lot of square roots in geometry. Okay, so we're going to rationalize the denominator. Okay, so right now, the denominator is what we call an irrational number. We have square root of 2 on the bottom. So we want to make that into a rational number, something like 2 or 4 or whatever. Okay. Yeah, so what we do is we multiply. You guys remember how we, like if I had 3/5 plus 1/2, do you guys remember how to get common denominators? We multiply by like 2 over 2 and 5 over 5, right? It's kind of the same thing here. It's kind of like we're changing the denominator, but we're not changing the actual number. So we're going to multiply by root 2 over root 2. Because when I have root 2 times root 2 on the bottom, so go ahead and find the bottom. Yeah, root 2 times root 2 is root 4, which is 2, a rational number, right? So we're going to have 4 root 2 all over 2. Oops, I got a little sloppy. So 4 root 2 all over 2. Okay, and then our last step is to simplify if possible. So what if I had 4x divided by 2? How would I simplify that? 2x, right? Same thing here. Think about the root 2 as being a variable. So if I had 4 root 2 divided by 2, I just get 2 root 2, and that's my answer. So we reduce out the 4 and the 2. But we don't do anything with the root 2 because it's just kind of like a variable on the side, 4x divided by 2. It's kind of like when you multiply numbers and then divide by a single number, you can just divide one of those numbers by the item. All right, so that's called rationalizing the denominator. So let's talk about, this is your math history fact of the day. I feel like math history is very fascinating because mathematicians are very strange. They're weird people. There's a lot of like really strange things that happen in math history. This isn't a really strange story, but it's kind of an interesting one, okay? It tells you why we do this. So if I had 4 over root 2 and I didn't have a calculator, so back in the day, imagine not having a calculator and finding all these different things. If you had 4 divided by root 2, I at least know that root 2 is 1.414 something. It goes on forever, never ends. So would you want to do this long division problem? No. That would be miserable, wouldn't it? You'd be like, okay, I think 2 goes in, and then I have 2.828, and I'm going to subtract, right? And it would take a very, very long time. Do we agree that that's nasty? We don't want to do that? All right, so 4 over root 2, we rewrote. We said it was 2 times root 2. If you know that root 2 is 1.414, dot, 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 what is 2 times root 2? 2.828. Does that make sense? Can you all do that in your head? Exactly. Okay, so this is why we rationalized denominators back in the day, because we didn't have calculators and we didn't have a magical button that we could just hit square root of 2. Okay, so it made things a lot easier when finding the approximation for that value. All right, so 15 over root 3. So if I have 15 over root 3, I'm going to multiply by root 3 over root 3 like that. So I'm going to have 15 root 3 all over 3, which is 5 root 3 when I reduce. So the 15 and the 3 reduce down. All right, same thing on the next one. So we're going to multiply by what? Root 5 over root 5. So we get negative 25 root 5 all over 5, and we reduce it down. So if I had negative 25x over 5, it would be negative 5x, right? So it's negative 5 root 5. You guys close that door. It's getting a little loud out there in the hallway. All right, and then you don't always have to do this, though. So the next one, I personally would not rationalize. I would not multiply by root 6, because I don't really know what 162 times 6 is, and that sounds like it's going to not be fun, okay? But I can verify, I can see, oh, does 162, is it divisible by 6? Yeah. Do you guys know how to test if something's divisible by 6? If it's divisible by 3 and 2, right? So we definitely know it's an even number. It's divisible by 2. How do I know that 162 is divisible by 3? You add them together, 1, 6, and 2 add up to be 9. And then that's a multiple of 3, right? You can divide that by 3. So therefore, it's divisible by 3. It's also divisible by 9. It's a 9 trick, right? So what I would do is I would just simplify before you even start, and I would take 162 and divide out by 6. So you can do that off to the side. You get 2, and then you have 12. I don't know why I wrote a 5 there, so 42. So I get 7, So it's negative square root of 27. Now do I leave it like that? No, because 27 has a perfect square that goes into it. So think about the factors. Michael, you with me? So, yeah, because we just took it in. We did the square root of all of it. All right, so I have the square root of 9, square root of 3. So I get negative 3 root 3. And that's our answer. Okay, so before we move on to the other ones, I want to show you one more. Yeah?
If there's like a negative that ends up to be inside the radical,
We're not going to do the negatives inside the radical yet. We will later on in the chapter. That's going to involve something called imaginary numbers. But right now, it's no real solution. All right, so one last thing. So sometimes I have students that get a little confused on questions like this. So if I have 2 over root 8, and we're trying to rationalize, you don't have to go as big as the number root 8. Because root 8, we could simplify it down. It could become 2 root 2, right? So let's think about it. If I have root 8 on the bottom, I don't want to multiply by root 8 and root 8. What do I want to multiply by instead? Square root of 2 over square root of 2. Do you guys see it? You want to make it as small as possible. Kind of like with getting common denominators for fractions, right? You don't want to, like, if you had like 5 and 10 as denominators, you don't want to make them 50, right? You want to make it as small as possible. So in this case, we would get 2 root 2 all over root 16, which is 4. And then we would reduce out, and we'd say, okay, 2 and 4 reduce out to become 1/2. So it's a 1 on top, 2 on bottom. So root 2 over 2 would be the answer. Does that make sense? So go smaller. Don't go really big with these. All right, and the last thing we have is kind of a preview of the next section. But like I said, the next section is going to be kind of tricky because it's going to involve variables as well, like x's, y's, z's. And it's also, we're going to have absolute values in certain instances. So we'll talk about all of the weird cases with that. But it says, what if we have the cube roots or fourth roots? What do these mean? So if I have the cube root of 27, all right, we can still do the factor tree. And that's kind of why I like this method, because it works for these as well. But now instead of looking for a group of 2 items, so pair, we're going to look for a group of 3 items. So we have 3 times 3 times 3, right? Colton. So 3 times 3 times 3, that means that when I take the cube root of 27, I'm going to get 3. But if I have 162, we break out up the 162, it goes into 2 and 81. I have 9 and 9. I have 3 times 3, 3 times 3. So now I have the cube root. So I want to look for a set of 3. So I have 3 3s. But now I have extra stuff, right? So just like before, that extra stuff stays inside the root. So when I have 3 times 3 times 3, that's 27. We just talked about the cube root of 27. It's 3. We just did that. So for this one, I'm going to have a 3 on the outside. And then what am I going to have on the right side of it? I'm going to have a 6. Is it going to look like this? No. There should be like a little tiny 3, right? That's called the index. Right? A lot of people forget that little tiny number. Okay, so don't forget if you started out with cube root, you still have a cube root. All right, fourth root of 32. Do you guys remember 32 was 5 2's? So 2 times 2 times 2 times 2 times 2. So if I'm taking the fourth root, I'm going to look for a set of 4 items. So 2 times 2 times 2, 2 times 2 times 2 times 2 is 16, right? And the fourth root of 16 is 2 then. So I have a 2 on the outside. And what do I have on the right side? So fourth root of 2, right? So don't forget your little 4. Yeah, cool.
Why don't you, like when you're squaring, why don't you put 2 over
2 over the, oh, yeah, why? So he's saying for a square root, why do we not put a little 2? There's a lot of things in math like this where we just like leave things off for the most basic term. Like with logarithms, we're going to learn logarithms. Usually we do like log base 7, but when it's log base 10, we don't put a little like 10 there. So some things it's just shortcut basically. We just are lazy. So one of them doesn't have anything and it's the 2. All right, so this next one, so 96. So we're going to have 8 and 12, 2, 2, 2, 4 and 3. So 2, 2, 3, and then our 2, 2, 2. So we're looking for 5 2's right there. Sometimes I have to do like around another term, like something like that. So I have 5 2's. So I'm going to get a 2 on the outside, and then I have the fifth root of 3 left on the outside. Okay, does that all make sense? You guys get that? So if I was previewing for the next section, if I had the cube root of 27 x cubed y to the 8th z to the 9th, do you guys see we would have 3? We'd have an x. How many y's would we be able to pull out? If we have 8 items, how many sets of 3? We'd have 2 sets of 3, so we'd have a y times a y, so y squared. How many would be left on the inside? So if I had 8, 1, 2, 3, 4, 5, 6, 7, 8, how many sets of 3? 2 sets of 3, and how many are left on the inside? 2, so I have y squared. And then z to the third, right? So that's what we're going to be doing on Monday. Okay, but then if we have an even root, we're going to have things that have absolute values as well. Crazy. Can you believe that? All right, I'm going to stop.